तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello and welcome again to all of you to the lecture sequence on the course on computer graphics. In the last two lectures, we have discussed the algorithm for line drawing, in which we had seen the Bressenham's algorithm on midpoint criteria to evaluate the next midpoint and to find out whether the next selected point is among the one out of the east or the northeast pixels to be put on the line. And remember, we are working on a discretized environment or digitized space, as you may call it, and we were also working on the constraint first that the algorithm works out points only in the first octant, and that's why the choice is between east and northeast. The first octant means that typically we are moving from left bottom of the screen to the right top. Slope of the line is less than 1. And towards the end of the last lecture, we had also seen how to take care of the other octants. That means if the slope is more than 1 or it is negative or the starting order of the point is different. That means if you have to move from the starting point at the top right to your bottom left on the screen, and how to draw the line. So we have to swap the points and change the increment from positive y to +1 to y -1 and things like that. So I think you have worked out based on the steps I have given to swap the roles from other octants and bring it to the first octant and then apply the same algorithm. So you need to apply an override for the other 7 octants, and then when the line is simplified to a situation of drawing a line on the first octant only, we apply the Bressenham's sequence of steps, the iterative loop from the left bottom to the right top of the screen, slope less than 1. Towards the very end of the lecture, from where I will basically continue today, we had also discussed in brief the situation what happens when you try to draw a line on a digitized space and what are the problems. And the main problem which came forward with the examples which we had shown in the last class and we are going to show today again is the effect of staircasing or aliasing or jaggies. Correct? We don't have a very smooth line, and you typically have a very the effect of a staircasing effect of the line drawn. So we start with that point from there onwards, where we left off in the last class, and there were. And the main 3 issues which we see here, along with that we'll see a few other issues as well today, is the effect of staircasing on the left. As you see, we have taken the same example of a line drawn from a point 5,8 to 9,11. As in the last class, we worked out this example and we came across these 3 points on the screen, and this blue line on the top left basically shows the line, which is actually the analog line, I would say, or the straight line, but the points which were selected by the algorithm, or even if you use the round function, you get the same sequence of points, and you see that the effect of staircasing or aliasing as it is called. Okay, so that's one of the problems which we have. We will not discuss the solution in this section today, but we will just talk about methods of how to reduce this staircasing effect. And these are the what are called the special effects of line drawing, which will try to give you a smooth nature. There are problems when we try to draw fat lines, because this line typically, as you see here, or the blue dotted line from bottom right to top left is a pixel, one pixel width, but if you need to draw lines which are more than 1, maybe 2 or 3 pixels wide, and you may get a scenario which is like this, which may not be ideal. That's the problem with fat lines or thicker lines as they are called. And then of course you have the problem of endpoint ordering of a line, where these 3 lines are drawn with 3 different colors. They are very wide and thick. One is the red line, another is the blue line here, and then you have the yellow line. And in such a situation, the problem which mainly comes is that what do you do with the endpoint? How do you draw the endpoint? Because if you draw the red colored line and on then top the blue color line, and then of course the yellow, the point comes is this common end junctions. There are 2 junctions of the lines in this case, whether you would like to put a color red or blue in this case, or in this case blue or yellow, or a combination of that. That is what you have to decide to maintain the continuity, so that the line looks very ideal. So these are the 3 problems associated with lines, and we'll take these solutions to these cases, specifically in the case of aliasing or the staircasing, try to see how to solve that. But to give an idea of how to reduce the effect of aliasing, we look into the next slide, where this is another example of a snapshot taken from one picture, where you see 2 different lines and the effect of staircasing in each. As you see here, the blue dots are the ones which have been chosen by the Bressenham's midpoint line algorithm here, and this is zoomed out or zoomed into basically larger dots, with a larger resolution on the right hand side. You see a fair set of points selected here, and typically, as you see, almost there is no point which strictly lies on the line. At the maximum you may find one, but not strictly. So you will have this effect of staircasing, and the question is, when you start to see this line in a high resolution screen and zoom into it, you typically will see this effect, and it may appear very bad to the user. So it may not appear very nice and neat and uniform. The thickness may be also varying depending upon the spacing of these pixels, respective pixels on the screen as you progress along the line. One way, we will not discuss an algorithm here to reduce the effect of aliasing, of what is called the anti-aliasing method. In fact, there are a lot of concepts based on even Fourier transformed in the spectral domain which can talk about anti-aliasing in signal processing theory, but with, we will keep ourselves to the computer graphics scenario in digitized space and try to see an example of how to reduce aliasing or reducing the staircasing effect. One way to do that is to vary the intensity of pixels around the points which have been selected by Bressenham's. Let us look at this example where we see a line is drawn from a pixel 1 1 to a pixel 10 4. Okay, slope is less than 1, the line is in the first quadrant. As you can see, we are attempting to draw a line which is more than 1 pixel wide, or even if it is 1 pixel wide, what we try to do is that we take a few adjacent pixels with respect to each pixel and then shade those pixels with a lesser color. Lesser intensity. In this case, of course, we are drawing a dark pixel on a white background, but it could be the reverse. That means you may have a dark background and drawing a white pixel. So whatever case may be, we are talking of a contrast, white on black or black on white. In this case, we are talking of black on white background. So the deepest intensity will be on those pixels which exactly lie on the center of the line. And as you see that the pixels which are separated out or towards the border of the line, they will start having lesser and lesser intensity. In this case, of course, they will start to becoming whiter rather than being dark. And now the question comes is, of course, which pixels do you select? That is one question which ought to be thought of, which we will discuss in special effects towards the end of this course. But suppose the pixel is selected, the neighborhood pixels which have to be shaded with a lesser amount of intensity than the one which is actually on the center of the line. A simple method can be used to find out what should be the intensity of the border pixels which are adjacent pixels to the true not falling exactly on the center of the line. A simple way of trying to find out is the following. You actually visualize that the pixel has a finite square unit area. As you see, each pixel is shaded by a square unit area, completely dark or gray or lighter ones, and depending upon the amount of area coverage, the amount of the area of the pixel square unit block which is inside the line, which is about 1 or 2 pixels wide in this case, assuming that this red rectangular strip basically shows the true line which we are trying to draw, and we just calculate actually how much of the square area or unit of this pixel is lying within this rectangular strip, and based on the amount of area which is inside, that is the factor which you use to shade the line. So it's simple. So if this is a line which is fairly thick, and then there are pixels which are lying within the line which have been selected by Bressenham's, and there are a few adjacent pixels pixels and we want to shade those adjacent pixels which are on the border of that line, more pixels are taken with lesser intensity compared to the center one. So the center one which is within that line strip will have the maximum area coverage in terms of the unit area which is within the line strip, that will have the maximum area and that will have the maximum intensity, black or white, whatever the case may be, whereas adjacent pixels will have less coverage. In fact, that means that the part of the rectangular strip will be overlapping with the square area which is adjacent, and we just calculate the amount of square area overlap between the rectangular strip and unit pixel. The larger the area overlap, more is the intensity, lesser is the amount of area overlap, lesser is the intensity. So if you look back based on this concept, as you can see that the pixels which are almost or exactly on the center are going to have darker, deeper intensity or black in this case, and those which are on the border will have lesser amount of overlap, and that's what is going to cause them to give lesser intensity. So the area overlap is one case. Of course, this area overlap function typically when they take in terms of you can use different type of models in terms of Gaussian or rectangular parallelepiped. We will talk this in special effects to see how different type of smoothing effects, rather how different type of effects of area overlap or even volume overlap can create different type of uniformness in the line. So this is one of the most standard techniques used to avoid aliasing, and we'll probably talk about this more in terms of what we call as special effects in terms of additional topics which I will cover at the end. Since this course, today's talk and the last two were on scanline drawing, we will go back to algorithm and of scanline drawings and curves in this course of the lecture. Okay, there are a few more points which have to be discussed, and the next point talks about intersection of a line with the vertical edge of the clipped rectangle. Again, I should repeat here that we have not covered the concept of clipping algorithms, but let us say in this case I am trying to illustrate a scenario where the blue line is the actual line and then there is a rectangular strip, a border. We are seeing the left and the bottom part of the rectangular area or coverage which will be clipping that line. So we don't need a part of the line which is to the left of the point Q. What is the point Q? Q is the intersection of this blue line with the vertical line x equal to x min, as you can see here. And we need to clip the line at this point Q and don't show pixels to the left of Q. We only need pixels to the right of Q because the line portion of the line which is on the left hand side of the point Q is outside the clipped area. This is the clipped area. Let us say we are looking into the left edge of the clipped rectangle and the bottom edge which is y equal to y mean of the clipped rectangle, and without applying the clipping algorithm for this line, we are trying to visualize what could be the problem if I am trying to clip this line with x equal to x min. The left edge is what is bothering us, and we will see, because what will happen is we don't want points to the left of the point Q, the pixels to glow, but we want the point to start from the pixel P. Okay, so the first point will be the pixel P which we want, the next point will be E and so on. Now what will happen is instead of Q you can automatically select P because that is the nearest round function. So when you are actually doing a scanline algorithm, the point P which is probably the northeast pixel with respect to the previous one will be selected by Bresenham's. So the point says here that there is no problem in this case to round off the starting point. We are talking of the starting point Q, is it? That is not a starting point in a discretized environment because that's a fractional number. M multiplied by x min plus b is the y coordinate of the point P, and x equal to x min is the x coordinate of point Q. So we are bothered about y coordinate of point Q, which is the point. Of course, P is the nearest to Q. So in terms of Bresenham's midpoint criteria, the point will lie over the midpoint below Q, and P will be selected. So so the statement, let us read it. It says that no problem in this case to round off the starting point, as that would have been a point selected by the midpoint criteria too. So P is selected. That's not a problem. But the next problem which comes is, yes, of course we select P. How to select P? It's very simple. Select P by rounding the intersection point coordinates at Q. So evaluate the y coordinates at point Q as given by m times x min plus b and round that function, it will give you P. So that's very straightforward thing. But what is the other problem? Okay. What about D start? You remember we had an initial variable, we had a decision variable D, and it needed an initialized condition or a starting value which we called as D start, and that D start will go wrong if you initialize the algorithm from P. if you initialize the algorithm from P and then scan convert, okay, the scan convert means apply the Bresenham's midpoint criteria iteratively, apply the midpoint criteria, look at the next east and northeast and so on. But if you start from P instead of Q somehow, which is basically going to happen because Q is a floating point, P is an integer number of both x and y coordinates. So if you start from P, you are basically changing the initial variable dy. What was dy? Remember y2 minus y1, and hence you are adjusting the original slope of the line. So this is a dangerous ploy to make, to change the d start from P, because the line itself will change. Instead of the blue line passing through P, which was the original line, the line will tend to appear to start from P. It may have a slightly different slope, but a different slope. That is the main problem, and that could cause some other pixels being selected as you apply the Bresenham's criteria from P onwards. So what do you do after P? Of course, P is selected by rounding off, but what about the d start? The concept is very simple. Start by initializing from d of m. So d of d is a variable which is evaluated at the midpoint. So don't start from d of p, because that will change. Start by initializing from d of m, that is the midpoint criteria in the next column, x min plus 1 after clipping. So you do a clipping, round off q to p, and then start by initializing d from the midpoint criteria. Start to evaluate it from here, okay, at x min plus 1. So that will help you to actually get rid of this point here from key. You actually apply the d of m by using the original values of dx and dy, and what will happen in this next case, in this example as shown in the figure, is if you see that the midpoint is lying above the line, E, and the E will be the next east pixel, will be the next pixel which will be selected, and so on. So once the d is initialized correctly at x min plus 1, which is the next line passing through northeast and east, you don't have a problem of a wrong initialization of d start. So clippings, you must be very careful. Okay, so we had seen two problems now in aliasing, and we know, if not algorithmically, the method to overcome aliasing a little bit, and we have seen how clipping could create problems in Bresenham's, and you have to be careful of starting with the d value in case you are clipping a line. That means you have a line and you are clipping it and you want to start at one point and then go ahead and don't bother about the rest of the line. So the clipping does create a problem, and you have to be careful when you start the initial variable d. Let us look at another example, or another problem of drawing a line, what we will call as a very shallow line, or a line with a very small slope. The value of m is equal to, well, it is between 0 to 1, but it is very small, approaching 0. It is not equal to 0, but it is a very small value. It could be a fractional, of course a fractional number, and very small one. And of course, there is absolutely no problem and no restriction of applying Bresenham's algorithm for any value of m, between, as long as it is in 0, 1, 1. You will get the correct values of the integer pixels along the path from the left hand starting point to the top right, as long as the value of m is between 0 to 1. Even if the value is close to 1 or close to 0, there is absolutely not going to be any problem. But if the line is going to be shallow, you do have problems with clipping. In addition to the clipping problem discussed earlier, we do have problems here. What is the problem? Let us look into the slide once again. We are talking of intersection of a shallow line with the horizontal edge of the clip rectangle. So the clip rectangle is, again, the left edge of the clip rectangle is x equal to x min, the left edge, and the horizontal edge is the y equal to y min line. Y is equal to y min line as marked here. This line in the middle, there are three lines which have been shown: y equal to y min plus 1, y is equal to y min minus 1. So y equal to y min is the horizontal clip edge of the line, and the left edge is x equal to x min. So what we are interested now to do is to clip the line and show points of the line which are inside the clip rectangle. And if we carefully see here, neglect the color for the timing and see the dots, as you can see here that points which are on and within the clip rectangle are marked by this brownish color here. There are 4 pixels on y equal to y min and 4 pixels on y equal to y min plus 1. Now the pixels which will be selected by the straight line by Bresenham's algorithm without clipping are these 4 pixels marked in purple color at y equal to y min plus y equal to y min minus 1, that is the bottom horizontal line which is below the horizontal clipped line of the horizontal edge of the clipped rectangle. So, these 4 pixels would have been selected, then you would have selected these 4 pixels, and then you would have the middle 4 pixels out of that 2 are marked as B, A and B. We will see why they are significantly marked, and those 4 pixels lie on y equal to y min, that is the horizontal edge, and y equal to y min plus 1, you will also have 4 pixels and so on. So, if you are interested in clipping now, the problem which will first come is you will be tempted to find the intersection point of the straight line and y equal to y min line, and that will give you the point A, correct, because that the point A is the closest round off integer value, as you can see in the figure, of the straight line and the horizontal clip line. So, you will be tempted to start from A and close shut off all the other pixels. Okay, start from A, have these 2 pixels, and then go on and get the 4 pixels and so on. There are 2 problems which could occur here. There are 2 problems. First of all, changing the slope of the line, and then at the edge what might happen is the line will abruptly end, because I would like to have the 2 pixels left of A along with B, which should also be a part of the line, because those would have been selected also by Bresenham's and they fall on and within. I remember I keep repeating on and within the clipped rectangle. So, all points selected by Bresenham's which lie also on the horizontal edge must be selected. So, the question is, how do you select these 2 pixels to the left of A, one of them which is the B. In fact, the B is marked because that is the starting point, should be the starting point of the line on the bottom horizontal edge of the clipped rectangle, and whereas A is the intersection point. Okay. So, automatically A selection is obvious and you might faultily start with A, but ideally to give the shallow effect of the line you should start with B. So, this is the problem of intersection of a shallow line with the horizontal edge of the clipped rectangle, and we will try to see how we can avoid this. That means start from B rather than starting from A. The solution is in the next slide. I hope you have drawn the figure by now, otherwise please draw it. There are 3 lines, y equals y min, y equal to y min plus 1 and y equal to y min minus 1. Do not worry about the left edge which is x equal to x min, we are bothered about the horizontal edge. There are 4 pixels marked here on y equal to y min minus 1, 4 pixels marked by Bresenham's on y equal to y min itself, that is the horizontal edge of interest, and 4 pixels also marked and shown here at y equal to y min plus 1. And the problem is, again I repeat, how to start from B rather than starting from A, because starting from A is very obvious choice, but not the correct choice. I should repeat it again, obvious choice, because that is the intersection point of the line A and the horizontal line y equal to y min, but I do not want to start with A, because you will be throwing off 2 legitimate and legal points, correct points obtained by Bresenham on the horizontal clip edge, which are to the left of B, left of A to be precise, and these 2 points must also be selected along with the other. So, all the brown points, that is brown colored points to the on y equal to y min plus 1 and also on the horizontal edge y equals to y min, all these 8 points must be selected, not only the 6 points starting from A to the right hand side. Okay. So, intersection, we had the problem of intersection of a line with the edge, and then rounding off produces B. Rounding off produces, I am sorry, A not B. Okay. So, if you take the intersection of the line with the horizontal edge and round off the coordinates, you are basically starting from A and not B, and that is the problem. And to get rid of this problem, that means to get B and the pixel between A and B as well as a part of the clipped line, basically I want to start with the B. Okay. And what is basically done is you need to obtain the intersection of the line with y min minus half and then round off and then get the coordinates of B. Let us see how it works. Remember what we have to do, the solution says obtain intersection of the line with the horizontal line y min minus half. That y min minus half line should lie between, it is a horizontal line, between y min and y min minus 1, and then you need to have an intersection of the line with this y min minus half and then round off. So, this is the formula to obtain the x intersection for y min, and let us go back to this figure and see what this basically means. Here, come back. So, intersection of the line with y equals y min was giving us A, which is correct up to that point, but we also need to get the 2 points to the left. So, you see here the dotted line, the dashed line between y equals y mean and y equal to y mean minus 1. This line is y mean minus 1, that is y equal to y mean, y coordinates is going up vertically, and the dashed line in between is the y equals y mean minus half, correct. If that is the horizontal line which is y equals y mean minus half, intersection of that line with the line being drawn on the screen, or the scan line as it is called, will give you this intersection point, but the coordinates of that intersection point are going to be floating point numbers. Coordinate of that intersection point is going to be a floating point number. So, what you need to do is calculate this in floating point, yes, all right, but then round off. You need at least to start with one round function in both these cases. In the previous problem as well, and in this current problem, you need to evaluate these coordinates and then round off to get the coordinates of B, which is going to be your starting point. Okay? So, B is going to be a starting point. I repeat the equation again, please note it down. You can get B by rounding off x at y mean minus half and not of x at y mean. If you evaluate x at y mean from the equation, you will start from the point A and not B, but if you use this formula as we have seen in the figure, you will start with the correct point A and also the point pixel A and B, as many of them will be selected, and this is the starting point of B. So, this is the problem, and of course, the D start, the initial value of D must also be followed in a similar manner as I discussed in the previous problem. You should not change the starting point so that the value of the slope of the line and the dy, both of them change. That is not correct. You have to start with the formula which has been given earlier for the D start to basically ensure that the clipping, the slope of the line. So, basically you evaluate the D at the next midpoint and start evaluating. That is the key idea. So, do that for D start, but in addition to D start, you have a problem in some cases, specifically for what is called as a shallow line, the line with a very small or negligible slope, which is almost horizontal but not exactly m is equal to 0 case where it is purely horizontal. Then of course, we do not have any problem, but m is slightly more than 0, it is a small positive value, let us say, then you have a problem when you clip that line. If you are not clipping, of course, there is no problem. Besson-Helms will work with any value of m, however small value of me, because we are working in the integer space, there is absolutely no problem here. But when you clip, you have problem with two cases. One is basically the problem that where do you start, because some points may actually unintentionally fall outside where they are supposed to lying on the edge. You start neglecting that if you do not do a correct round function, and then the initial value of D start. We know how to do the D start, that means evaluate the value of the D or start the initial value of the D at the next midpoint. That is how you do with the D, and typically also we had seen when you need to start correctly, you evaluate by rounding off the value at the previous value of y mean. Okay, so these are the two special cases which one must take care in terms of clipping for a straight line, and we wind up the scanline algorithm for straight line or line drawing right now. I mean, we have discussed the DD algorithm earlier, and then of course the Besson-Helms criteria, Besson-Helms algorithm steps which is based on integer arithmetic. We have taken an example to illustrate how it works, and then of course we discussed the problems of aliasing Jaggis, fat lines, the endpoint effects, and of course the problems of clipping, where we discussed the starting value, and the clipping problem where some points might unintentionally fall outside the range. Okay, so these were in detail the discussion we had till today on scanline algorithm, and we move towards the next kind of algorithms on curves, and we start with the simplest curve which we know is this circle. Of course, we will discuss also ellipses, but since ellipse circle is a special case of an ellipse, if you are able to draw an ellipse, you should be able to draw a circle, but we will see later on why we are discussing circle specifically separately again for the first time next, and then move on to ellipses. And once you have algorithms for scan line like we have drawn for a straight line, if you have algorithms to draw a circle or an ellipse, you should be able to draw any arc. So these are the three types of scanline algorithms. First, we have discussed line, so we have discussed the special effects, we have discussed the cases of problems of intersection lines with clip edges and all that, and now we move on to circle drawing. So that is the next stage. We move over to circle drawing, and that is how to draw a circle on a screen, and we will see an example. If you look into the picture, you see that you have to have the points on the circumference of the circle, and you have to start somewhere. In this case, we assume that you start with the topmost point of the circle, that is the intersection of the circle with the vertical line which is passing through the center of the circle. So, we start with that point, move to the next and so on. So, unlike this scan line for line drawing, where we were drawing lines between slope 0 and 1, and that means points were in the first octant. You remember the octant, 8 of those which divide the entire space into 8 equal parts. Okay, in 2D space, we also can visualize octants here in the case of a circle. And if you look at the figure again, you should be able to tell me in which octant these points are lying. They are not in the first octant anymore, isn't it? They are lying in the, yes, the second octant. They are lying on the second octant, and so we will draw points only in the second octant, and points in the second octant will start from the topmost point here and keep going. I have drawn 3 points only and stop at a particular point, and the last point in the second octant will have a special property. You can guess easily, but I am telling you right now that the coordinates of that last point in the second octant, which lies on the circumference of the circle, will have its x coordinates equal to y coordinates. Y coordinate values, what is the coordinates of the first point? Assuming the center of the circle is lying at the origin, don't worry if it is not lying in the origin. Let us start with the assumption, the most simplest case, where it is lying in the origin. So, if the origin is 0, 0 and the radius is equal to r, so the coordinates of the first point will be 0, r, correct? 0, r will be the coordinates of the first point. So, x coordinate will be 0, y coordinate will be r. And as you keep moving along the circumference of the circle from the first point to the second point to the third point and so on, what will happen is the x coordinate will start increasing and y coordinate can only decrease. If, okay, y coordinates start with r and decrease, x coordinates start with 0 and increase, and the last point in the second octant will have a scenario where the x coordinate will be equal to y coordinate, and that point will be at exactly 45-degree orientation with respect to the center of the circle. Now, if the center is of the circle is not in the origin, this is absolutely no problem. We have already seen lots of transformations in 2D and 3D, and we know how to manipulate figures on the screen. And so, if it is not on the origin, there is absolutely no problem. Actually, we shift the origin to the center of the circle, or shift the center of the circle to the origin, draw the circle and then shift it back. We know all these manipulations when we studied about transformation. So, we apply that. So, we apply 2 constraints here to draw a circle. First of all, the origin is the center of the circle, okay, and you start with the topmost point with coordinates 0, r and move to the right along the circumference. So, we are moving in the second octant, and once you have covered the points on the second octant, I believe you should be able to visualize already how the other octants symmetrically, how the other points on the other 7 octants can easily be obtained. Of course, we will show the algorithm how to do that, as we have done for a scan line when we drew points only in the first octant, but actually got the points in the other 7 octants also, isn't it? So, we did that swap, if you remember, swap and interchange type of operations, okay, increment, decrement. Here in this case, if you pick up the points on the circumference which lies on the second octant only, the other octants also can be symmetrically generated, because a circle is highly symmetric, not only in 4 parts but also in 8 parts. Okay. So, let us see what is happening in the second octant. As the best, we are also going to apply blindly the Bresenham's midpoint criteria for a case of a circle. So, it means the following: if you are working on the second octant and xpyp is the point of the current iteration which has been selected by at the previous stage of iteration, let us say, if that is the point which has been selected, the next point can only be one out of east or southeast depending upon where the line passes. If it is to the top of the point M, or M is below the circumference of this line, in this case it is a curve, but I will call it as a line. So, do not confuse, it is not a straight line, but it is a line, let us say, or an arc, but I will use the word arc and line interchangeably. So, this line or arc, if it is on top of M, you select E. Okay, or if the M is on top of the line and the line passes below M, then you select southeast. So, that is a very simple criteria, like Bresenham's case of a line. Evaluate the midpoint with respect to the arc of the line, find out if M is below or above the line, and then and that will tell you whether the line is close to the, in this case, east and southeast. In the case of a line for the first octant, the choice was east and northeast for you, and in this case when the circumference is coming down in the second octant, obviously the choice after the current iteration is going to be either east or southeast, because the curve curve is going to fall in the second octant. So choice is here east and southeast. In the case of a line, we had east and northeast. Here it is falling in the second octant, there it was going up in the first octant. So we had east and northeast after the current choice. In this case of a second octant, after the current choice, the curve is going down along the circumference. So you have to choose between east and southeast for the line. Okay, so this is what is going to happen in the second octant. And if you look back into the figure, if we have chosen east in the current iteration after you have evaluated the xp, yp, and then you have moved over to select east, say in this case as the line is above m or m is below the line, then if you have selected E, the next midpoint criteria where you have to evaluate is this point m of E, midpoint after E, or if you have selected southeast, if the line was below m, if it had been below m, then you would have selected southeast. The next midpoint evaluation, the next to next iteration would have been midpoint of southeast or MSE, which is this point as marked here. So we know that the choice basically at any stage of iteration is between east and southeast, and we are working on the second octant. So please remember that now the choice is between east and southeast pixels at any stage of iteration. So a few points to be considered on circle drawing. We will go through a few points. It only considers circles centered at the origin with an integer radius. We have, let's assume that we have an integer radius and the center is at the origin. We can apply translations to get non-origin centered circles. We also discussed this. That means if the center of the circle is not at the origin, we either translate the origin or translate the circle such that the center is shifted to the origin or the origin is shifted to the center of the circle, and then everything falls in place. Well, now we have to look into the equation for a circle. Okay, if you look into the slide, an explicit equation as it is called for a circle, that means given a particular value of x, if you want to obtain a value of y, remember unlike in the case of a line, you can have two values of y. For a given value of x, r is the radius of a circle, is the plus or minus square root of r square minus x square. R square minus x square, square root of that is going to be value of y. Of course, in one case it will be two different points of y are two different octants, that is all. But we are going to use, since the midpoint criteria, we will use the functional form f of xy is equal to 0, which is called the implicit equation for a line. The implicit equation of a line in the case of f of xy is equal to 0, for the case of a line also we had seen, and now in the case of a circle, the implicit equation, not the explicit, the implicit equation becomes x square plus y square minus r square equal to 0. The equation of a line is, everybody knows, x square plus y square equal to r square, like mx y equal to mx plus b. So shift everything to the left hand side and make y minus mx minus b is equal to 0 in the case of a line. In the case of a circle, we make x square plus y square minus r square equal to 0. So that is the implicit equation of a line. And implicit equations are used extensively in advanced modeling, not only in circle drawing. In fact, not only for curves, but for surfaces in 3D, planes and surfaces in 3D. Whatever is a line or a circle or a curve in 2D is basically an on-planar or a planar surface in 3D. Implicit equations are used for extensively for advanced modeling in computer graphics. We will come across these equations later on when we also talked about solid modeling and advanced concepts of modeling. A typical example for using implicit equations for a surface model is the liquid metal creature from the movie Terminator 2. Okay, I hope you have seen there are lots of, I did say entertainment games and movies is one very good application, or one of the most widely used applications of computer graphics. And those who had seen the movie, the picture Terminator 2 Judgment Day, would have seen this liquid metal creature which melts itself into, through various parts, physical bodies, is done with the help of, this is an example of implicit equations. Coming back to circle drawing, which we were discussing, if you look into the point here as mentioned in the slide, we use the symmetry. What is the symmetry of the circle we are talking about? One only needs to calculate one octant, and in this case we have already decided to start with the second octant. Start from the point 0, r and calculate in the second octant, and after completing the second octant, one can get points in the other 7 octants as follows. As we did for a line, we computed in the first octant when slope was less than 1, and then we knew how to get the other 7 points. And I am sorry, For the case of a line, even if the line was not in the first octant, we knew what to do to shift the line in this case to the first octant. In the case of a circle, it's not that. In fact, if you want to draw a complete circle, points on the circumference of the circle will be spread over all the 8 octants, in the 2D space. And so instead of, and since there is a lot of symmetry in the way the points in the circles are distributed, if you can get 1/8 of the circumference, that means points on the second octant only, by symmetry you can obtain the points in the other 7 octants, and that is what is going to be discussed here. As you can see, we have put a small piece of pseudocode for what we call as a draw circle at x comma y. This is not the line circle drawing algorithm, but it says that I am using symmetry, and if I have already obtained a point x comma y using Bressenham's criteria for the second octant, then I can get points in the other octant using this set of plot point. Assuming you have a graphical specification for plotting a point at x comma y, and that x comma y coordinates of the point on the circumference of the circle or on the circle is obtained at the current stage of iteration by the Bressenham's algorithm. All the other 7 points can be easily obtained by symmetry. You can see the symmetric nature of the plot point commands, where we are either swapping the positions of x and y, or changing the sign of x or y, or both in, and generating all the other 7 different cases for drawing the line. And just this next figure will show you what this basically means in terms of getting the point. The point x comma y, the first point is shown in a different color than the other 7 points. And x comma y is obtained at, say, at current point of iteration in the second octant, and after this is obtained, you can obtain all the other 1, 2, 3, 4, 5, 6, 7 points by symmetry in the other 7 octants. By from x y, you can go to first to y comma x, then change the sign of y to get minus y comma x, then change the sign of x to get minus y comma x, and then finally change again the sign of x to get minus y comma x. From x comma y, you can change the sign of only y to get x minus y, then you change the sign of x to get minus x comma y, and then finally you change the sign of y again to get minus x comma y. So there are, this is the paths are shown to illustrate the sequence, but you can pick up any sequence. In fact, you can absolutely use the plot point commands from xy to yx to minus y comma x and so on, but this shows the path in which the symmetricity is maintained, and it shows how symmetric the points are with respect to the horizontal and vertical axis of this 4-way symmetry is shown. 8-way symmetry is also visible here. That means all the other points in the 7 octants are obtained after you have obtained the point in the first octant only. X comma y is in the first octant, all the 7 points are obtained. And I repeat it again, this is a code to obtain the points only in the 7 octants, not for the Bressenham. Bressenham's gives you x comma y, I repeat again, and this is a code for an overhead draw circle routine, which will generate, basically plot the points, all the 8 points in the screen corresponding to points on the 8 octants obtained from the second octant point x comma y. Second octant point is x comma y, and all the other points in all the other 7 octants are obtained using the symmetrical nature. So that's very easy, straightforward, and in fact it's much easy to visualize this scenario, and also the code as given here in the previous slide, that you can see that the flip nature of x and y, or the sign of x and y, or both are changed as I was talking about, and the points here are symmetric. This is much easier than the visualization of all the other 7 octants in the case of a line, because in the other case of a line you basically had to do a little bit of manipulation, jugglery with the xy coordinates or the positions of the line. If the line has more slope more than 1, or the starting order is different, you have to do a little bit of adjustment to bring the line into this first octant, then draw it, and then generate the point which will originally generate the points back in the other quadrants. In this case, you just find the points always in the second octant, and the other points are drawn using the algorithm as given here. Well, we now slowly move actually into the midpoint circle algorithm, and let us see how much time we have to get into the criteria as possible today, and then continue in the next class. So we will calculate points in the second octant as given here. and after the point, a single point in the second octant, or all the points in the second octant are available, we use the draw circle code which we have given here, which produces and calculates the rest of the points using symmetry, which we have just seen now. So, points in the second octant have to be drawn from the equation of the circle, and we also know now that the choice is between east and southeast pixels, because the origin has been shifted to the center of the circle, or the center of the circle has been shifted to the origin. So, we are starting always from 0, r, keep choosing between east and southeast. Let us look at the implicit equation of a circle. It is given as, we have seen that earlier, f of x y is equal to x square plus y square minus r square equal to 0. Okay. And the midpoint criteria we also know from Bessenham's. In the case of a line, we apply the same logic. If the function value of fxy is more than 0, the point is outside the circle. If the value of f of xy is less than 0, then the point is inside the circle. Okay. This is easy for you to visualize. If you take a circle and take points exactly on the circumference of the circle, the value of the function value fxy will be equal to 0. So, assume you have a circle. Assume you have a circle and the circumference of the circle, and when you choose points on the circumference of the circle and substitute into the implicit equation f of xy equal to 0, which is given in this case for a circle as x square plus y square minus r square equal to 0. So, if the point is exactly on the circle, the value of x square plus y square will be equal to r square, which is very natural, and the value of fxy will be equal to 0, that we know. Now, if we choose a point inside the circle, not on the circumference, but within the area enclosed by the circumference, what will happen is the sum of the x square plus y square will be less than r square, and hence the value of the function f of xy, you remember the equation as given in the slide, x square plus y square minus r square equal to 0 is given. That is the implicit form of the equation of the circle, and if I choose a point which is inside the circle, the value of x square plus y square is going to be less than r square, and hence the value of the function will be negative. However, if I choose a point outside the circle, assuming this to be a circle, a small circle, and if I choose a point outside the circle, outside the circumference or area of the circle, then the value of x square plus y square will be more than r square, and the value of function will be more than 0. This is the concept similar to the case of a line. You also had a scenario of greater than or equal to 0 depending upon whether a point is above or below the line in the case of a straight line. Here it is below or above an arc. In fact, we logically have to think that it is within the circle or outside the circle. So, that is the condition. We look here, we have the functional value f of xy as given here, and you remember f of xy will be positive if the point is outside the circle, the value of f will be negative if the point is inside the circle. If the point is exactly on the circumference, which we actually have to find out what are those pixels which are the closest or on the circle, then the value of f of xy will be equal to 0. We start straight with the Bessenham's, because we know we already had ideas on what is the decision variable, what based on the functional value of the expression of a circle. So, we straight away we know the logic at each point of iteration starting from the first point. What we have to do? We have to evaluate in the next midpoint, take a decision based on the sign, update, choose, and again evaluate the next midpoint, and so on. Okay. So, look back. Again, in the case of the midpoint criteria for a circle, we use d old equal to f of m, where m is the next point. Now, what is the next midpoint, the first midpoint which comes? Well, given any point xp yp, we will see that figure again. We have seen earlier, xp yp is the current point, the next midpoint is xp plus 1, yp minus half. The first midpoint, when the first point which has been selected is 0, r, if you remember, that is the topmost point on the circle in the second octant. The next midpoint will be plus half r minus half, correct? I am sorry, plus 1 and r minus half, correct? Plus 1 and minus half is how the midpoint will be progressing depending upon east and southeast choice, of course. But again, if we go back to the slide, so xp yp, if it is the current point of interest, then the midpoint will be xp plus 1 yp minus half. Why? Because choice midpoint is between east and southeast pixels, unlike east and northeast in the case of a line. Remember, in the case of a line, when we had east and northeast, I keep switching between line and circle here. Please don't confuse, because I hope I assume that the line is in your mind and you should try to map that. In the case of a circle, the equations are just different, but the concept is exactly similar. In the case of a line, when the slope was more than 0 but less than 1, the choice was between east and northeast. So, the next midpoint was plus 1 plus half. Typically in the choices between east and southeast, the next midpoint will be plus 1 minus half. Okay, so that's one. So xp yp is the correspond in the current point of iteration. Next midpoint is xp plus 1 yp minus half. If you substitute these coordinates in the expression of x square plus y square minus r square equal to 0, you have the d old value as f of m equals xp plus 1 whole square plus yp minus half square minus r square. You can break open these brackets if you want and expand and get the polynomial form of this expression in two variables xp and yp, but don't do that. Keep that expression of fm and let us look at the next choices. If d is positive or equal to 0, as you see in the slide, the choice is d greater than or equal to 0, you choose southeast. Okay, so your choice is between east and southeast, and the next midpoint based on whether d is greater than equal to 0, the choice becomes southeast. Okay, and the next midpoint m nu will have to be incremented by plus 1. If you look into the slide, now you will find the next point is incremented by 1 along x and minus 1 along y, which gives the d nu. Okay, so the d nu is has to be the new variable of new value of the variable d, which is evaluated at the next midpoint m nu. If you choose southeast, you are basically have to increment by plus 1 along x and minus 1 along y to get the d nu. What is the next d nu? Well, we know what is d nu and we know what is d old. So what we do is we look at the first order derivative of delta d under the choice that we have chosen southeast, and that is d nu minus d old given by xp plus 2, provided you have chosen southeast. So it is plus 1 and then plus 1 again, and yp minus 3 by 2, because minus half we talked about earlier, and then minus 1 3 by 2 minus the d old, and the difference will be, if you subtract these two expressions of xp plus 2 and yp minus 2 for f and xp plus 1, that is the d old expression here, d new expression here, you will get the expression as 2xp minus 2yp plus 5. Okay, so that is the increment in d delta d under the condition that you have chosen southeast. Okay, let's see what happens if you choose east. If you choose east under the condition that the value of d is less than 0 or negative, you are choosing east because we will see in the figure, because when the value of d is negative, the midpoint is basically below the line, or the point or the circle is passing over the midpoint and closer to east, and so you have chosen east. So the next midpoint m nu must be incremented by 1 along x and nothing by y, which gives d nu, and the value of d nu under the condition that you have chosen east is given by d nu minus d old delta d east. The increment provided you have chosen east will be given as d nu minus d old is xp plus 2 yp minus half instead of 3 by 2, because you remember in the case of southeast we were decrementing also y by 1, but not in this case anymore. Henceforth the difference in these two will be f of xp plus 2 yp minus half minus the d old value which was originally computed earlier, and the difference in the value of the first derivative under the condition that the east is chosen is xp twice into xp plus 3. Okay. The only point of contention now is what is going to be your d start. What is going to be your d start? The d value will be the first midpoint, and I did say that the first midpoint is 1 and r minus half, because the first point is 0 comma r, the next point midpoint is plus 1 and minus half. If you substitute in the value of f, you have 5 by 4 minus r. Okay, so that is the initial value of the d, and of course we do have a problem now, because as you can see, if xp yp are integer points, then the delta d, the first derivative, the first increment along for southeast and east are all integer quantities, all right, if you look into the expression, because xp yp are integers, so these two expressions are integers, but unfortunately d start will be a floating point number. This is easily avoided by the following. To get rid of this fraction for d start, what we substitute, you take a new variable h and define it as d minus 1 by 4, and that is what you get as h start, a new variable for h as 1 minus r, because if you take h is equal to d minus 1/4 and substitute the value of d start, what was d start in the previous expression? 5 by 4 minus r. So take the value of d start, substitute in d, you will get 1 minus r. and if since r is an integer, h of start is an integer, and you keep incrementing h by the first derivative differential delta d east and southeast. You have to make, you can say now the next problem is you have to compare h with minus 1 by 4, which is a fraction, correct, because if d is equal to 0, that is the decision variable which you are evaluating for the midpoint, we are comparing with 0, h will have value minus 1/4. So you have to compare with minus 1/4, which is also neither good. Why? Because we want all integer arithmetic if possible, both in terms of incrementing, computation, row and round function, initial value also to start an integer and compare with integers, in this case 0. So you, instead of comparing with h with minus 1 by 4, what we do, since h is initialized to and incremented by integers, we can just do this by comparing h with 0. That 1 by 4 factor will not affect you at all, because as if although h notionally has to be compared with a floating point number, but it will be incremented by integers and decremented by integers only. So you don't at all compare with floating point numbers, you always compare the h with integer value which is 0. So we have reduced this d start and replaced it by an h start, and it is an integer again, and we are comparing only with 0. That means we look for the values of h, whether it is positive or negative. It is a new decision variable h. Instead of d we have an h, we know the relation between h and d, so we keep incrementing by delta d east and southeast, which are again integers, start with an integer value, increment with integers, increment decrement depending upon the sign and the value of delta d, and compare also with a value 0. So there is no comparison, no addition, no computation of floating point numbers in this case. It is all integer arithmetic done for a circle. Remember, although the circle had a nonlinear equation, unlike a straight line which was a linear form y equal to mx plus c, we had square terms in both x, y and r, but still we were able to do with integer arithmetic even with Bresenham's criteria for midpoint. So we will stop at this point and continue from here onwards, where we have understood to apply the midpoint criteria for a circle, and we look at the first version of the midpoint algorithm for drawing a circle with the starting integer arithmetic and then increment by integers. Thank you very much.